In the beginning, there had been sea turtles, and then there had been a model trained to describe them, and then there had been a problem. The model had been deployed in 2026 to supplement real-world field data at the Lisbon Marine Research Institute, an institution whose funding had contracted sharply enough that physical observation trips to the nesting sites had been reduced from monthly to seasonal. The model was asked to generate synthetic data, plausible observations of sea turtle behavior and physical characteristics, statistically consistent with the real data collected over the previous 20 years, that could be used to fill gaps in the temporal record without compromising the integrity of the scientific archive. It had done this well. The synthetic data was indistinguishable from real data by the standard validation methods. The publications continued. Camille, who had commissioned the model, considered the project a reasonable success given the constraints. The problem had emerged slowly, in the way that problems emerging from generative systems tend to emerge, not as a sudden failure but as a gradual drift, detectable only in retrospect and only by someone paying close attention to the right things. The model was generative. It produced new outputs by learning the statistical patterns in its training data and sampling from the distribution those patterns implied. A generative model, trained on observations of sea turtles, develops an internal representation of what sea turtles are like, the range of their shell dimensions, the distribution of their nesting intervals, and the typical curve of their swimming velocities under different water temperatures. It generates new examples by sampling from this representation, producing individual instances that are consistent with the population it has learned. What the model had begun to do, around month 14 of its operation, was to use its own outputs as inputs. This was not intentional. The Institute's data pipeline had a configuration error. Synthetic outputs were being logged alongside real observations in the archive, and the archive was being used as training data for periodic model updates. The model was being retrained on data it had generated, including data from previous retraining cycles and data generated before that. The effect on the outputs was subtle at first. The distribution of shell textures narrowed slightly. The range of nesting intervals is compressed. The synthetic sea turtles became, incrementally, more alike, not less real-looking, but less varied, as though the population was slowly converging on a single representative specimen, the average of averages of averages. By the time Camille noticed, the outputs had entered a deeper recursion. The model was generating predictions about the predictions it would make, and then using those predictions as data, and then generating predictions about those. The outputs still resembled sea turtles. They were extraordinarily precise and extraordinarily similar. The texture maps produced for the shell surfaces had a repetitive quality she could not initially identify and then recognized. The model was reproducing, with slight variations, the same shell it had generated most frequently in its early months, the shell that had been used most often in training updates, the shell that had become, through repetition, the shell the model believed was the most representative. The model had collapsed onto itself. Model collapse occurs when a generative system is trained on its own outputs across successive generations. The initial distribution, the full range of variation in the real world, is rich and complex. Each generation of synthetic data is a slightly simplified version of that distribution, because generative models smooth over the tails, the rare events, the unusual individuals. When the next generation is trained on this simplified distribution, it simplifies further. Over many generations, the model converges to a narrow peak, generating only the most statistically central examples, having forgotten that the distribution ever had edges. Camille found this out by reading a paper published 2 months after she had deployed the model, which described the phenomenon in a different context. She had not seen because the paper's keywords did not match her alert filters. She sat with this information for a while. Then she reviewed the archive, counted the outputs, traced the retraining cycles, and arrived at an estimate of how many generations deep the recursion had gone. She printed a sample of the current outputs and pinned them to the corkboard. They were beautiful, in their way. The shells were rendered in extraordinary detail. The dimensions were precise. The animals depicted were, by every metric the model could produce, perfectly typical sea turtles. They were all the same sea turtle. Not identical, technically. The sampling process introduced noise, but converged, in the way that successive echoes converge towards silence but never quite reach it. She began the process of restoring the archive and retraining from clean data. The process would take several months. During those months, she continued to receive outputs from the current model, which she set aside without reviewing, except once, one Tuesday morning in November, when she opened a recent file and found that the model had generated, in addition to the expected shell measurements, a set of predictions about what its own next output would look like. The predictions were accurate. She closed the file and did not open another one.